Here's problem 8.21. A 10 kilogram object is dropped from rest. After falling a distance of 50 meters, it has a speed of 26 meters per second. How much work is done by the dissipative air resistive force on the object during this descent? Okay, let's imagine what's going on here. Let's say we have an object, and we're going to drop it from point A, and it's going to fall and eventually reach point B. And that distance between the two is 50 meters. And when it reaches point B, it's going to have a velocity going down like this. So it will have kinetic energy. And what else? Oh, the whole time there is a dissipative force, say a force of friction, against the motion as it's falling. Alright, so that's the setup. We want to employ the one equation to rule them all. The kinetic energy at A plus potential energy at A plus any work done along the way will equal the kinetic energy at B plus the potential energy at B. Question is, which if any of these terms might actually be zero? And we know that we started from rest, so our kinetic energy will be zero. We're going to define our lower height at point B as being our zero height, and there's no springs involved, so the potential energy at B is going to be zero. There is going to be work done along the way, because that's what we want to find. What is the work done by the friction in the air? So we know the kinetic energy at B, and there will be potential energy at A, so that's it. The work done along the way will equal the kinetic energy at B minus the potential energy at A. That's going to be 1/2 the mass times the velocity at B squared minus the mass times G times the height at A. That's going to be 1/2 times 10 kilograms. At B, it's moving 26 meters per second times 10, 9.8. Height at A was 50 meters above that point, and this is negative 1,520 joules. So that is the work done along the way. Since it's only being done by the resistive force, that is the work done by the air resistive force. If we wanted to, we could actually figure out what that air resistive force is, because we know that this work should equal the force times distance cosine the angle between the two. With the resistive force going up and the displacement going down, this angle theta is going to be 180 degrees. So this is going to actually be equal to the resistive force times d times a -1 cosine of 180. That means that the resistive force is going to equal the work on the system divided by negative work on the system divided by d, which would be a negative 1,520 divided by 50, and that is positive 30.4 newtons. So that is the resistive force. That's not what we were asked to find, but it's always nice to know. We were asked to find the work done by that resistive force, and that was a negative 1,520 joules.